Introduction.
Good morning, teacher.
Good morning, students. Today we learn organic chemistry.
Teacher, what is organic chemistry?
Organic chemistry is the branch of chemistry that involves the study of carbon and hydrogen containing compounds.
Teacher, how the carbon-carbon atoms are attached?
The carbon-carbon atoms are attached by single bond, double bond or triple bond, and the functional group present on the organic compound decides its chemical nature.
Teacher, what is functional group?
It is a group of atoms in an organic compound responsible for the chemical reactions of that compound. In this lesson, you will learn organic chemistry and some basic principles. Objectives. At the end of this lesson, you will be able to define tetravalency of carbon, describe formation of pi bond, represent organic compound through complete, condensed and bond line structural formulas, represent organic compound in 3D, classify organic compound, describe nomenclature of organic compound. Tetravalence of carbon, shapes of organic compounds. Organic chemistry is the study of hydrocarbons and other compounds regarded as derivatives of hydrocarbons. Some organic compounds may also contain elements like nitrogen, oxygen, sulfur, phosphorus, halogen, etc. besides carbon and hydrogen. The shapes of carbon compounds. A carbon atom has 4 electrons in its outermost shell. So, it needs 4 more electrons to complete its octet. A carbon atom can complete its octet only by sharing its valence electrons with other atoms. As a result, carbon atom forms 4 covalent bonds by sharing valence electrons with other atoms. This is known as tetravalency of carbon. For example, methane, ethene, ethine. Carbon can participate in hybridization and form sp, sp2, sp3 hybrid orbitals. Hybridization also affects the bond length and bond enthalpy in organic compounds. The sp hybrid orbital has more s character and hence it is closer to nucleus and forms stronger bond than sp3 orbital. The sp2 hybrid orbital is an intermediate orbital between sp and sp3. Some characteristic features of pi bonds. Pi bond is formed by the overlapping of p orbitals on adjacent atoms. The p orbitals should be parallel to each other and both perpendicular to the plane of the molecule. Pi bond inhibits the free rotation of carbon-carbon double bond. Pi bond provides the electron charge cloud in the molecules which have multiple bonds. Structural representations of organic compounds. Complete, condensed and bond line structural formulas. The structure of organic compounds can be represented by Lewis or dot structure, dash structure, condensed structure and bond line structures. The Lewis or dot structures can be simplified by using dash. Single dash represents single bond. For example, propane. Double dash represents double bond. For example, propene. Triple dash represents triple bond. For example, propyne. These structural representations are called complete structural formulas. Structural representations of organic compounds. In the condensed structural formula, each carbon atom is written separately and following each carbon atom, other atoms are listed that are bonded to that carbon atom. For example, complete structural formula. Its condensed structural formula can be written as bond line structures. In this, carbon and hydrogen atom are not shown, but only the bonds between the carbon-carbon atoms are shown in zigzag fashion. The atoms other than carbon and hydrogen are shown in the structure, and the terminals denote methyl group. For example, butyl chloride, propene, cyclohexane, diethyl ether, dimethylamine. Three-dimensional representation of organic molecules. Three-dimensional structures of organic molecule on paper can be represented by using solid and dashed wedge formula. The solid wedge represents a bond projecting from the paper towards the observer. The dashed wedge represents a bond away from observer. A simple line represents a bond that lies in the plane of paper. For example, methane. Classification of organic compounds. Organic compounds can be grouped into acyclic or open-chain compounds and cyclic or closed-chain or ring compounds. Cyclic compounds can be further divided into homocyclic or carbocyclic compounds and heterocyclic compounds. Homocyclic can be further divided into alicyclic and aromatic compounds. Aromatic compounds can be further divided into benzenoid and non-benzenoid compounds. Acyclic or open-chain compounds. Acyclic compounds are the open-chain structures, and they are also called as aliphatic compounds. Alicyclic or closed-chain or ring compounds. Alicyclic are the organic compounds in which three or more carbon atoms are linked together in a ring. Aromatic compounds. Aromatic compounds are the organic compounds which contain benzene ring and other ring compounds. Benzenoid aromatic compounds are benzene, naphthalene, toluene, indene, biphenyl, anthracene, phenanthracene, etc. Non-benzenoid aromatic compounds are tropylene, etc. Heterocyclic aromatic compounds. A heterocyclic compound is an organic compound in which one or more of the carbon atoms have been replaced by an atom other than carbon. Typical heteroatoms are nitrogen, oxygen and sulfur. Functional group. It is a specific group of atoms in a molecule responsible for the chemical reactions of that molecule. Homologous series. A homologous series may be defined as a series of structurally similar compounds, each member of which differs from preceding or succeeding member by one group, CH2. The members of the series are known as homologs. Nomenclature of organic compounds. Nomenclature is the system of naming of organic compounds. In the early stages of organic chemistry, the organic compounds were named from the source from which they were prepared. For example, the name acetic acid was derived from vinegar because the Latin word for vinegar is acetum. Methyl alcohol was named wood spirit as it was obtained from the destructive distillation of wood. These names of organic compounds are called common names or trivial names. The IUPAC system of nomenclature. IUPAC stands for International Union of Pure and Applied Chemistry. By using this system, we can give a systematic name to an organic compound. The systematic name of organic compound can be derived by identifying parent chain, functional group, and branch chain. We also add prefixes and suffixes through which the parent name is used to get the actual name. IUPAC nomenclature of alkanes. Straight-chain hydrocarbons. The names of these compounds are based on their parent chain structure, and their name ends with a suffix -ane. Branched-chain hydrocarbons. In this, small carbon chains are attached to carbon atoms of parent chain. These small carbon chains are called alkyl groups. To name branched chain hydrocarbon, The names of alkyl group attached to carbon atoms of parent chain prefix to the name of parent alkane. An alkyl group is formed from saturated hydrocarbon by removing one hydrogen atom from carbon. To name alkyl group, we substitute YL. Some abbreviations are used for alkyl group, such as Me for methyl, Et for ethyl. Alkyl can also have branched chain structures such as isopropyl, tet-butyl. Nomenclature of branched chain alkanes. The rules for naming are given below. First, we identify the longest chain of the carbon in the molecule. The carbon atoms in the parent chain are numbered. It helps to locate the carbon atoms with attached alkyl group. The numbering in the parent chain is done in such a way that the branched carbon atom get the lowest possible numbers. That means the numbering in the given carbon chain is from left to right. After that, the names of the alkyl are prefixed to the names of the parent alkane. Thus, the name of the given organic compound is 3-ethyl 1-methyl heptane. Nomenclature of branched chain alkanes. If the substituent groups are similar, then the numbers are separated by comma and prefixes are used such as given below. If the two substituents are at the same position from both the ends, then the lower number is given to the carbon which comes first in the alphabetical listing. For example, 2-ethyl 5-methyl hexane. Some IUPAC common names are: common name is isopropyl, its IUPAC name is 1-methyl ethyl, and its structure is this. Common name is sec-butyl, its IUPAC name is 1-methyl propyl, and its structure is this. Common name is isobutyl, its IUPAC name is 2-methyl propyl, and its structure is this. Common name is tert-butyl, its IUPAC name is 1,1-dimethyl ethyl, and its structure is this. Common name is neopentyl, its IUPAC name is 2,2-dimethyl propyl, and its structure is this. Nomenclature of branched chain alkanes. To name the multi-substituted compound, the following rules must also be remembered. If there are two chains of equal number of carbons, then the chain which contains more number of side chains is selected. The numbering is done from the end which is nearest to the substituent. For example, the IUPAC name of the given compound is 4,2,2-dimethyl propyl octane. Cyclic compounds. The single-bonded monocyclic compounds are named by prefixing cyclo-straight chain alkane. For example, cyclobutane, cyclopentane, cyclohexane. Nomenclature of organic compounds having functional group S. Functional group defines the chemical reactive nature of organic molecule. In polyfunctional compounds, one functional group is chosen as principal functional group and the remaining are treated as substituents with appropriate prefixes. Some functional groups are given below in the table. Decreasing order of priority for some functional group is carboxylic acids, acid anhydrides, esters, acid chlorides, amides, nitriles, aldehydes, nitriles, aldehydes, ketones, alcohols, amines, alkenes, alkynes, halo, nitro, alkoxy, alkyl. For example, let us write the IUPAC name of the following organic compound. Here, the word root is but, but, and primary suffix is ane, ane. There are two functional groups, ketone and alcohol. Ketone gets preference over alcohol group. Thus, the secondary suffix is 1. The prefixes are methyl and hydroxyl. Thus, the name is 3-hydroxy, 3-methyl-butane, 2,1. Nomenclature of substituted benzene compounds. To name the substituted benzene compounds, these compounds are named by attaching the name of the substituent as a prefix to the benzene. For example, bromobenzene, tert-butylbenzene, nitrobenzene. If more than one substituent is attached to the benzene ring, then the naming is done by numbering the carbon atoms of the benzene ring in such a way that substituents get the lowest possible numbers. For example, 1,2-dinitrobenzene, 1,3-dinitrobenzene, 1,4-dinitrobenzene. In trivial system, ortho O, meta M, and para P terms are used as prefixes to represent the relative positions 1, 2, 1, 3, and 1, 4 respectively. For example, ortho-dinitrobenzene, meta-dinitrobenzene, para-dinitrobenzene. Nomenclature of substituted benzene compounds. For more than di-substituted benzene ring, ortho, meta and para cannot be used as prefixes, and the compounds are named by locating the substituents on the benzene ring on the lowest possible number. One substituent of the compound is given number 1, and then the direction of numbering is chosen in such a way that the next substituent gets the lower number. The names of the substituents appear in alphabetical order. For example, we assign number 1 to fluorine so that nitro gets 2 and ethyl gets 4. This compound can be named in alphabetical order as 4-ethyl, 1-fluoro, 2-nitrobenzene. When benzene ring is linked to an alkane with functional group, then the benzene ring is treated as substituent. The term phenyl is used to indicate C6H5. Did you know? Messenger spacecraft of NASA has uncovered evidence that not only does water ice exist on the surface of the planet Mercury, but in many places, this ice appears to be covered in a 10 centimeters thick layer of soot-like organic material. Summary. Let us summarize what we have learnt. Organic chemistry is the study of hydrocarbons and other compounds regarded as derivatives of hydrocarbons. Carbon is a tetravalent compound. Pi bond is formed by the overlapping of p orbitals on adjacent atoms. Organic compounds can be represented by complete, condensed, and bond-line structural formulas. In 3D representation, the solid wedge represents a bond projecting from the paper towards the observer, and the dashed wedge represents a bond away from observer. Acyclic compounds are the open chain structures, whereas alicyclic are the organic compounds which are linked together in a ring. Functional group is a specific group of atoms in a molecule responsible for the chemical reactions of that molecule. Nomenclature is the system of naming of organic compounds. In trivial system, ortho, meta and para terms are used as prefixes to represent the relative positions 1, 2, 1, 3 and 1, 4 of a benzene ring respectively. Introduction. Today we learn isomers and concepts used in organic reaction mechanism. Anybody knows about isomers? Anyone? No? Okay, I will tell you. The organic compounds which have same molecular formula but different configurations are called isomers. The examples of isomers are dimethyl ether and ethanol. They have same molecular formula but different configuration.
Teacher, what is reaction mechanism?
Reaction mechanism is a sequence of steps during which chemical reactions occur. In this lesson, you will learn isomers and fundamental concepts in organic reaction mechanisms. Objectives. At the end of this lesson, you will be able to describe isomerism and its types, explain fundamental concepts in organic reaction mechanisms. Isomerism. Existence of sets of two or more compounds with same molecular formulas but different configurations and hence different properties. The compounds are called isomers. Different types of isomerisms are: isomerism can be grouped into structural and stereoisomerism. Structural isomerism can be subdivided into chain isomerism, position isomerism, functional isomerism, meta-isomerism. Stereoisomerism further categorized into geometrical and optical isomerism. Structural isomerism. Structural isomers are the molecules which have the same molecular formula but have different arrangement of atoms. Chain isomerism. Chain isomers have same molecular formula but have different order in which carbon atoms are bonded to each other. Structural isomerism. Position isomerism. This isomerism is due to the difference in the position of functional group in the same chain, is termed as position isomerism. Functional group isomerism. They have same molecular formula but different functional groups. Metamerism. This isomerism arises due to non-uniform distribution of carbon atoms on either side of functional group. For example, methyl propyl ether and diethyl ether. Stereoisomerism. Stereoisomers have the same molecular formula and same connectivity, but different orientations of their atoms in space. Stereoisomerism can be grouped into geometrical and optical isomerism. Fundamental concepts in organic reaction mechanism. Organic reactions are chemical reactions involving organic compounds. The organic molecule is also termed as substrate, reacts with attacking reagent, and forms intermediate and then the final product. A reaction mechanism is the step-by-step sequence of elementary reactions by which overall chemical change occurs. Fission of a covalent bond. A covalent bond may be broken by two ways: heterolytic cleavage, homolytic cleavage. In heterolytic cleavage, the bonding pair of electrons remains with one of the two fragments between which the bond is broken. For example, all carbocations have a positive charge on the carbon atom. Classification of carbocation. Primary carbocations. In this, the carbon atom which carries positive charge is attached to only one alkyl group. These are also called 1-degree carbocation. Secondary carbocations. In this, the carbon atom which carries positive charge is attached to two alkyl groups. These are also called 2-degree carbocation. Tertiary carbocations. In this, the carbon atom which carries positive charge is attached to three alkyl groups. These are also called 3-degree carbocation. Order of stability of carbocations is: a carbanion is negatively charged molecule that induces a carbon atom with negative charge. The simplest carbanion is the methide ion can be derived from methane by a loss of proton. Homolytic cleavage. When a covalent bond breaks in such a way that each atom retains one electron of the bond, the process is called homolytic cleavage or homolysis. It often produces free radicals. The movement of single electron is shown by a fish hook arrow. Nucleophiles and electrophiles. The reagents which are electron-rich, such as chloride ion, are called nucleophiles because they seek centers of positive charge, that is, nucleus. Nucleophilicity can be defined as the tendency of an atom to donate electrons to an atom. The reagents which are electron deficient, such as carbocations, are referred to as electrophiles. Electrophilicity can be defined as tendency of an atom to accept electrons from an atom. Electron movement in organic reactions. Curly arrows are used to show the movement of electrons. The tail of the arrow indicates the location from where the electron pair is shifted, and the head of the arrow indicates the location on which the electron pair is moved. Movement of single electron is indicated by half-headed curved arrow. Electron displacement effects in covalent bonds. An attacking reagent can be positively or negatively charged. Therefore, the reagent will attack a substrate only when the substrate develops an opposite charge and the substrate can develop some polarity by the displacement of electrons. Such displacement of electrons in the substrate molecule is referred to electron displacement effect. Inductive effect. It is a permanent displacement of electrons which originate due to the difference in the electronegativity of the two atoms. Let us consider a chain of carbon atom in which the terminal carbon atom is joined to a chlorine atom. Chlorine is more electronegative than the carbon. Therefore, the electron pair in the covalent bond between the chlorine atom and C1 atom will be displaced towards the chlorine atom, due to which chlorine atom acquires a small negative charge and C1 acquires a small positive charge. Now C1 is slightly positively charged, so it attracts the electron pair, forming covalent bond between C1 and C2, due to which C2 acquires a small positive charge, but the charge is smaller than that on C1 because the effect is passed from C1 to C2. Similarly, C3 also acquires a small positive charge which is smaller than the charge on C2. This type of shift of electron along a carbon chain is known as the inductive effect. The symbol I is used to denote the inductive effect. The groups which are electron withdrawing, they are said to cause negative I effect, and the electron releasing groups are said to cause positive I effect. Resonance structure. The structure of some compounds cannot be represented by single Lewis structure. For example, toluene. Resonance structures represent two or more Lewis structures that differ only in the placement of their electrons. Organic molecule, benzene, cannot be represented by a single Lewis structure as it has alternating single and double bond. The structure of benzene ring is resonance hybrid of structures first and second called resonating structures. Another example of resonating structures is acetate ion. The energy difference between the actual structure of resonance hybrid and the lowest energy resonance structure is called resonance energy. Following rules must be applied in writing resonating structures. The same positions of nuclei and the same number of unpaired electrons. Resonance effect. Delocalization of pi electrons over more than one atom is termed as resonance or mesomeric effect. It is symbolized by capital R or capital M. It is of two types: positive resonance effect, positive R effect. This effect is shown by the groups which release electrons to the rest of the organic molecules by delocalization of pi electrons. For example, aniline. Negative resonance effect, negative R effect. This effect is shown by the groups which withdraw electrons from the rest of the organic molecules by delocalization of pi electrons. For example, nitrobenzene. Electromeric effect, E effect. When a compound containing double or triple bond is exposed to attack by an electrophilic reagent, the electron pair is transferred completely from one atom to another. The atom to which the electron pair is transferred becomes negatively charged and the other atoms become positively charged. This is a temporary effect. As the reagent is removed, the organic molecules revert to their original state. The effect which causes temporary polarization in a substrate molecule containing a multiple bond by shifting of an electron pair from one atom to the other under the influence of an electrophilic reagent is called electromeric effect. Types of electromeric effect. Two types of electromeric effect: positive electromeric effect, positive E effect. If the pi electrons of double or triple bond are transferred to that atom to which the reagents get attached ultimately, this effect is called positive E effect. For example, addition of acids to alkenes. Negative electromeric effect, negative E effect. If the pi electrons of double or triple bond are transferred to that atom to which the attacking reagent does not get attached, this effect is called negative electromeric effect. For example, addition of cyanide ion to the carbonyl group. Hyperconjugation. Delocalization of sigma electrons through sigma pi or sigma p overlap known as hyperconjugation. The sigma bond in conjugation with the pi bond or sigma bond in conjugation with the p orbital participates in delocalization and thus stabilizes the system. For example, in propene there are 3 CH sigma bonds of CH3 group which are in conjugation with the pi bond. The sigma electrons are transferred to adjacent carbon-carbon bond and pi electrons are shifted to terminal CH2 carbon. 3 contributing structures are possible for propene as it has 3 CH sigma bonds. Due to participation of sigma electrons in delocalization, the bond between carbon and hydrogen does not exist in contributing structures, due to which hyperconjugation is also referred to as NO bond resonance. Did you know? In the hydrogen molecule, the sigma bond was formed by the overlap of two 1s orbitals. Moses Gomberg is the founder of radical chemistry. Summary. Let us summarize what we have learnt. The compounds with the same molecular formulas but different configurations are called isomers. Types of isomerism are structural isomerism and stereoisomerism. A reaction mechanism is the step-by-step sequence of elementary reactions by which overall chemical change occurs. A covalent bond may be broken by heterolytic and homolytic cleavage. In heterolytic cleavage, the bonding pair of electrons remains with one of the two fragments between which the bond is broken. When covalent bond breaks in such a way that each atom retains one electron of the bond, the process is called homolytic cleavage. Nucleophilicity can be defined as the tendency of an atom to donate electrons to an atom. Electrophilicity can be defined as the tendency of an atom to accept electrons from an atom. Inductive effect is a permanent displacement of electrons which originate due to the difference in the electronegativity of two atoms. Delocalization of pi electrons over more than one atom is termed as resonance or mesomeric effect. The temporary polarization of an organic molecule containing a multiple bond due to the shifting of an electron pair is called electromeric effect. Delocalization of sigma electrons through sigma pi or sigma p overlap known as hyperconjugation. Introduction. Students, in the previous part we have learnt the isomerism and fundamental concepts used in the organic reaction mechanism, and today we learn the methods of purification of organic compounds. Some of the methods are sublimation, chromatography, distillation, etc.
Teacher, what is sublimation?
Sublimation is the process in which solid directly converts to vapor state without passing through liquid state upon heating. Now, can anybody tell me what is chromatography?
Teacher, chromatography is a technique used to separate and analyze a mixture of chemicals.
Very good, Aryan. Now we'll study the processes of purifications in detail. In this lesson, you will learn purification of organic compounds, qualitative and quantitative analysis of organic compounds. Objectives. At the end of this lesson, you will be able to describe methods of purification of organic compounds, explain qualitative analysis of organic compounds, describe quantitative analysis. Methods of purification of organic compounds. The various methods for the purification of organic compounds are sublimation, crystallization, distillation, differential extraction, and chromatography. Sublimation. Some solids change directly from the solid state to vapor state on heating. This process is termed as sublimation. It is used to separate sublimable organic compounds from non-sublimable compounds. The impure organic compound is heated in a dish covered with perforated asbestos sheet over which an inverted funnel is placed. The stem of the funnel is filled with cotton, and on heating, the part of the solid which sublimes passes through the holes in the asbestos sheet and condense on the cooler walls of the funnel. The non-sublime impurity. Crystallization. It is the most common way of purification of organic solids. It is based on the difference in the solubility of the organic compound and the solvent in which the organic compound is mixed. The impure substance is in powder form and then heated with the solvent in a flask. The amount of solvent should be just sufficient to dissolve the substance on heating. The hot saturated solution is then filtered with the hot water funnel. The hot water circulated in the outer funnel keeps the solution hot, and crystals cannot be formed in the funnel itself. The hot filtrate is cooled in the beaker and large crystals are obtained, and then the crystals are separated from the filtrate by means of filtration. Distillation. Distillation is a method for purifying liquids and separating mixtures of liquids into their individual components. On heating the liquid mixture in a flask, the components in the liquid which have low boiling point start vaporizing. The vapors are condensed in the condenser and the resulting liquid is collected in a receiver. The components of liquid which have higher boiling point vaporize later and the liquid can be collected separately. Fractional distillation. When the boiling points of the two liquids are very close, then simple distillation does not work. In that case, a fractionating column is used, which is long tube provides obstructions to the passage of the vapors upwards and to the passage of liquid downwards. The mixture of liquids A and B with 370 Kelvin and 380 Kelvin respectively boiling points is present in the flask. On heating the flask, the vapors obtained are more of A and less of B. As the vapors rise up in the fractionating column, the partially condensed liquid flows down. The vapors of B condense faster as compared to A, and the vapors moving up richer in A. The condensed liquid flowing down strikes the vapor and it consumes molecules of B. This process is repeated throughout the fractionating column, due to which the vapors escaping through the top of the column are almost of A and the liquid left in the flask almost of B. Distillation under reduced pressure. This process is used if the liquid has a tendency to decompose near its boiling point. The main neck of the flask is fitted with long capillary tube and the side neck fitted with thermometer. This side tube is connected to a condenser which is connected to the receiver at the other end. The receiver is connected to a pump which reduces the pressure. Under reduced pressure, the liquid will boil at a low temperature and the temperature of decomposition will not be reached. For example, glycerol boils with decomposition at 563 Kelvin, but if the pressure is reduced to 12 millimeters, it boils at 453 Kelvin without decomposition. Steam distillation. This method is used to separate the substances which are steam volatile and insoluble in water. This method based on the fact that a liquid boils at a temperature when its vapor pressure becomes equal to the atmospheric pressure and the vapor pressure of a mixture of two immiscible liquids is equal to the sum of the vapor pressures of the individual liquids. Steam is continuously passed through the compound which is required to be distilled. Steam heats the liquid and also condenses to water. After some time, the mixture of water and liquid starts boiling because the vapor pressure of the mixture becomes equal to the atmospheric pressure. The temperature at the instant is lower than the boiling point of the substance or that of water. The mixture of liquid and water is condensed and collected in a receiver which can be easily separated. Differential extraction. When organic compound is present in aqueous solution, then the organic compound is extracted by using a solvent in which organic compound is more soluble than water and the solvent is not miscible with water. If the organic compound is less soluble in a given solvent, then a very large quantity of solvent is required to extract a very small quantity of the compound. This technique is known as continuous extraction. Chromatography. Chromatography is a technique used to separate the components of a mixture to identify organic substances and examine their purity. Classification of chromatography. Adsorption chromatography, partition chromatography. Adsorption chromatography. Adsorption chromatography is based on differential absorption, that is, different compounds are absorbed on adsorbent such as solid, SiO2 gel or Al2O3 to different extent. Based on differential adsorption, there are two types: column chromatography and thin layer chromatography. Column chromatography. It is the process in which the mixture of various components, when passed through a column containing an adsorbent such as starch or charcoal, the different substances are absorbed to different degrees and thus they can be separated with the help of suitable solvent called eluent. Thin layer chromatography. It involves the spreading of the thin layer of adsorbent on a suitable support such as glass plate, etc. The glass plate is known as thin layer chromatography plate or chroma plate. The mixture to be separated is applied as a small spot from one end of the TLC plate. The glass plate is then placed in a closed jar which contains the solvent. As the solvent moves up in the jar, the components of the mixture move up along the plate to different distances depending on their degree of adsorption, and separation takes place. The relative adsorption of each component of the mixture is expressed by retention factor, that is RF value, which can be given as RF is equal to distance moved by the substance from the baseline by distance moved by the solvent from the baseline. Partition chromatography. Partition chromatography is a paper chromatography in which a special quality paper known as chromatography paper is used. Chromatography paper contains water trapped in it, which acts as the stationary phase. The chromatography paper is placed at the base with the mixture of solvents. The solvent acts as mobile phase. The solvent rises up in the paper and flows over the spot. The different components are separated according to their differing partition in the two phases. The developed paper strip is known as chromatogram. The colorless compounds may be observed either under UV light or by the use of an appropriate spray reagent. Qualitative analysis of organic compounds. Detection of carbon and hydrogen. Carbon and hydrogen are detected by heating the organic compound strongly with copper-2 oxide. The produced gases are passed through anhydrous copper sulfate and then passed into lime water in a test tube. If carbon is present, then it forms carbon dioxide, which turns the lime water milky. The reactions are as follows. Carbon in organic compound reacts with copper-2 oxide and produces copper and carbon dioxide. The produced carbon dioxide reacts with calcium hydroxide, which turns it milky, indicating the presence of carbon in organic compound. If hydrogen is present in the organic compound, then it forms water vapor, which passed over copper anhydrous sulfate turns it blue by forming CuSO4 5H2O. The reactions are as follows. Hydrogen in organic compound reacts with copper-2 oxide and produces copper and water. The produced water reacts with anhydrous copper sulfate, which turns blue by forming CuSO4 5H2O. Detection of other elements. Other elements such as nitrogen, sulfur, halogens and phosphorus in the organic compound can be detected by Lasigene's test. The elements in the organic compound fuse with the sodium metal. The reactions are as follows. When sodium reacts with various elements found in the organic compounds, then it forms sodium fusion extract. Test for nitrogen. On addition of ferrous sulfate to sodium extract, that is sodium cyanide, it produces sodium ferrocyanide. The ferric ions generated during the process react with ferrocyanide to form blue precipitate of ferric ferrocyanide. Test for sulfur. If sulfur is present in the organic compound, then it can be identified by the reaction of sodium fusion, that is sodium sulfide Na2S with sodium nitroprusside. Then Violet color indicates the presence of sulfur. Test for halogens. The presence of halogens is tested by acidifying a portion of sodium extract, that is NaX, with dilute nitric acid and adding silver nitrate. If a white precipitate is formed which is soluble in ammonium hydroxide, it indicates the presence of chlorine. If a yellow precipitate is formed which is sparingly soluble in ammonium hydroxide, it indicates the presence of bromine. If the formed yellow precipitate is insoluble in ammonium hydroxide, then it shows the presence of iodine. If nitrogen or sulfur has been detected, the solution must be boiled for a couple of minutes to expel HCN and H2S, which interfere with the test. Test for phosphorus. The presence of phosphorus can be detected by fusing the organic compound with sodium peroxide. The formed solution is treated with concentrated HNO3 and an excess solution of ammonium molybdate is added. A yellow precipitate indicates the presence of phosphorus. Quantitative analysis. Carbon and hydrogen. A sample of organic compound is heated to 700 degrees Celsius in a steam of pure dry oxygen and in the presence of copper-2 oxide. The hydrogen is oxidized to water and carbon to carbon dioxide. The amount of water produced is determined by passing it through anhydrous calcium chloride, and carbon dioxide is determined by passing it through solution of potassium hydroxide. The mass of hydrogen present in sample of organic compound will be 1/9, the increase in mass of the calcium chloride, and the mass of carbon will be 3/11, the increase in mass of the potassium hydroxide. Nitrogen. There are two ways for estimation of nitrogen: Dumas method and Geldel's method. Dumas method. A known mass of organic compound is heated with copper oxide in the atmosphere of carbon dioxide. Under these conditions, carbon and hydrogen are oxidized to carbon dioxide and water respectively, and nitrogen is set free. If any oxide of nitrogen is formed, it is reduced back to nitrogen by hot reduced copper. The gases produced are passed from potassium hydroxide solution through furnace. Potassium hydroxide absorbs carbon dioxide and nitrogen is collected in the upper portion of the tube. Percentage of nitrogen in organic compound whose mass is m, Gm is 28 into V into 100 divided by 22,400 into m, where V is the volume of nitrogen at STP. Geldel's method. In Geldel's method, nitrogen is estimated by ammonia gas. The organic compound is heated with sulfuric acid. Nitrogen in the organic compound is converted into ammonium sulfate. The ammonium sulfate is then heated with excess NaOH and it liberates ammonia. The produced ammonia is absorbed in standard solution of sulfuric acid. The produced ammonia can be estimated by the amount of sulfuric acid used in the reaction. It can be done by estimating the amount of sulfuric acid left after the absorption of ammonia by titrating it with standard alkali solution. The difference between the initial amount of sulfuric acid taken and the amount that left after the reaction provides the amount of acid reacted with ammonia. The percentage of nitrogen is 1.4 into m into 2 times of the difference between V and V1 by 2 divided by mass of organic compound, where V is equal to volume of H2SO4 taken in milliliters, V1 is equal to volume of NaOH in milliliters, M is equal to molarity of H2SO4. Halogens. Carius method. A known mass of organic substance is heated with fuming nitric acid and then silver nitrate is added in the tube called Carrius method. The formed silver halide is separated, washed, dried and weighed. Percentage of halogen. Atomic mass of X into M1 into 100 divided by molecular mass of AgX into M, where M1 is the mass of AgX formed and M is the mass of organic compound. Sulfur. A known mass of the organic substance is heated with fuming nitric acid. The sulfur is converted into sulfuric acid. The formed sulfuric acid is precipitated as barium sulfate by adding barium chloride. The precipitate is filtered, washed, dried and weighed. Percentage of sulfur. 32 into M1 into 100 divided by 233 into M, where M1 is the mass of barium sulfate formed and M is the mass of organic compound. Phosphorus. The organic compound containing phosphorus is heated with fuming nitric acid and phosphorus is oxidized to phosphoric acid. Phosphorus is precipitated as ammonium phosphomolybdate by addition of ammonia and ammonium molybdate. Percentage of phosphorus. 31 into M1 into 100 divided by 1877 into M, where M1 is the mass of ammonium phosphomolybdate and M is the mass of organic compound. Oxygen. The percentage of oxygen in an organic compound can be determined by the method of difference. All the elements in the organic compound except oxygen are estimated and the total of their percentages subtracted from 100 to get the percentage of oxygen. The organic compound is heated in the stream of nitrogen gas. The formed mixture of gases is passed through red-hot coke and oxygen gas is converted into carbon monoxide. Now the carbon monoxide is converted into carbon dioxide by mixing iodine pentoxide into the mixture. According to chemical reactions, the percentage of oxygen can be found as 16 into mass of carbon dioxide divided by 44 into mass of organic compound into 100. Did you know? Carbon occurs in all living organisms. Carbon is a nonmetal and that it can bond with itself and with many other chemical elements, forming nearly 10 million compounds. Summary. Let us summarize what we have learnt. Sublimation, crystallization, distillation, differential extraction, and chromatography are the methods for the purification of organic compounds. Carbon and hydrogen can be detected by heating the organic compound strongly with copper-2 oxide. Nitrogen, sulfur, and halogens can be detected by sodium fusion extract. The mass of hydrogen present in sample of organic compound will be 1/9, the increase in the mass of calcium chloride, and the mass of carbon will be 3/11, the increase in mass of the potassium hydroxide. Percentage of nitrogen in organic compound whose mass is mgm is 28 into V into 100 divided by 22,400 into m, where V is the volume of nitrogen at STP. Percentage of halogen in organic compound is atomic mass of X into M1 into 100 divided by molecular mass of AgX into M, where M1 is the mass of AgX formed and M is the mass of organic compound. Percentage of sulfur in organic compound is 32 into M1 into 100 divided by 233 into M, where M1 is the mass of barium sulfate formed and M is the mass of organic compound. Percentage of phosphorus in organic compound is 31 into M1 into 100 divided by 1877 into M, where M1 is the mass of ammonium phosphomolybdate and M is the mass of organic compound. Percentage of oxygen in organic compound is 16 into mass of carbon dioxide divided by 44 into mass of organic compound into 100.